This is the UKMT Senior Math Challenge from 2015. Let's just do it. We can see straight away here that this is of the form n squared minus n plus 1 times n minus 1. If you get given maths like this, the rule is you shouldn't be doing the maths, right? So you shouldn't be calculating these things. Write it in algebra in the form that it's in. And then this simplifies, of course, to this, which is just this, which means the answer is 1 no matter what these numbers were in the first place, which is very convenient. Times both sides of this equation by x, and we get this, and then we divide by 6 first, and then we square root, which gives us plus or minus 5. So the sum of the solutions is 0, because they add to 0. So in pounds per litre, initially it was 40 divided by 50, which is 0.8, and afterwards it was 50 divided by 40, which is 1.25. So we're sending 0.8 to 1.25. Now, 50% of 0.8 is 40, or 40 pence. So when we add that on, we get to 120. So a 50% increase on this is pretty close. So I'm just going to underline 56 and move straight on. I'm just there. I'm doing a 50% increase. But yeah, I think it's going to be this. I think this is too high. So let's go with it. Here we're going to just make up that this radius is 1, so a diameter of 2, which makes the big radius 2. So the area of the full thing is pi times 2 squared, so 4 pi, and the area of the small one is 1 pi. So therefore, this area here is 3 pi's. So the fraction of the area outside the circle is 3 pi over the whole circle itself is 4 pi, so that's 3/4, I guess. So yeah, we're fine. The n is the mean of these, so add these up and then divide by 3, because there are 3 of them, and we equal n. So you can just times by size by 3, and then take away 2n, and you just get n is 40 straight away. The sum of the digits of 40 is, of course, just 4. Now, 5 needs to be placed next to, you need to make prime numbers every time. So 5 plus 6 is 11. So 6 is one of the ones you want to put it next to. And that makes 12, that makes 13. So that's fine. So yeah, and then just check that there's no other options. That would make 14 and that would make 15. Okay, cool. So these are the only two we're allowed here. Next to 6, you could also put a 7 to make 13. And next to 8, you need to put a 9 to make 17. I don't think there are any more options. And it doesn't really matter. In this case, down here, the one we're missing is a 10. So we'll just go with that as the answer. I actually recommend practicing stuff that looks like this, just because it really helps you to sort out fractions that maybe look a bit like this in the middle of much bigger questions. Like here, for instance, just instantly knowing that essentially the answer to this is just these two combined together to make the denominator, so 6, and then these two to make the numerator. So this is 4 over 6, which is 2/3. And like here, the way that I would do this is just to jump the 4 up to the top, and then it's 4 over 2/3, which means the 3 jumps to the top, so then it makes 12 over 2, which is 6. Alternatively, 2/3 divided by 4 is 2/8, and which is a sixth, and then 1 over a sixth is 6, of course. But yeah, any kind of tricks like these is really helpful. Of course, a half divided by 3 is a sixth, and then you divide by 4 to make a 24th, which is obviously much smaller than this. I mean, this is the biggest one. You can do the others yourself if you want to. Here I would just also, you could just think about combining the 3 to the 4 to make 1/2 over 12, and then, of course, combine the 2 and the 12 to make 24. Same kind of idea. But yeah, you can work out the others doing some various tricks anyway. The answer is definitely B. It's way bigger than the others, so yeah. Okay, so I had some trouble with 8 because I hate nets. I basically refuse to teach them in my career, so I'm not very good at them because I never think about them ever. I think they're really dumb. But anyway, when we're looking at this picture here, you need 6 of these boxes because at least I do at least know that there are 6 sides on a cube. So you need to miss 3 of them out, essentially. No, 2 of them out. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 2 of them out, sorry. Now, I think that you need this one. Like, you just have to have this one. I just marked them with X's, the ones that you definitely need. The reason you need this one is because you can't, if you don't have this one, you can't have any of these 3 because they're not connected to the rest of the structure, or this one either, and you're missing too many. So you have to have that one. Likewise, you have to have this one because otherwise you're missing these 2. And this on its own, you can't, 1, 2, 3, 4, 5, 6, you can't have these 6 because this structure you can't use. Because if you think about folding this together, this one has nowhere to go once these 2 fold upwards, or whatever, however you're thinking about it, or vice versa, this one has nowhere to go. So yeah, you can't use these 3 together, which means this has to be used because you can't just ignore those 2. And then finally, this one also has to be used because, like I just said, you can't ignore both of these 2. You have to use at least one of them. But you can't just use this one on its own, right? Because it's not connected to the others properly. So it has to be, you have to therefore have this one and maybe this one as well, and we'll see. So there are 5 boxes left, and you need 3 of them to complete your cube. So I just 5 choose 3 and just said an upper bound is 10 here. And then I tried to just remove the ones that I didn't think could be made. For example, I don't think you can make this by choosing those 3, as I've already said. So that removes one of them. And I also don't think you can do it by choosing I think these 2 together, because when you try and fold these 3 up, like if you make that the base, these 2 the sides together, these 2 fold into the same place. So you can't have any configurations where those 2 are chosen together. So you can only have one of those. So that removes another 2 configurations, I think, because it removes this, this, and this, or this, and that. So that takes us down to 7. And then the last one to remove, what is the last configuration to move? I can't even remember. Is it something like, oh, neither of these, those 3, or did I say that one? So you can't have these 3 together. You can't have those 2 together. That removes 3. And then finally, you can't have this, this, and this. Oh, sorry. Having these 2 together removes 3 of them, actually, doesn't it? It removes this, this, and this, this, and this, that. So that's 3 of them gone, and then you can't have those 3 either. So that was 4 gone. So that's how I got to 6, I think. Yeah, like I said, really dumb. Don't like that question at all. But if you're good at nets, maybe you'll find it easier. I don't know. 4 different straight lines are drawn. The number of intersections are counted, essentially. You can draw this, and that's 1 intersection, so cross out this because that's something you can make. And then I drew this, and that's 4 of them, so cross out this. Then I drew this, and that's 3 of them, so that's assuming these are parallel. So that's this gone. So now I'm down to 2 and 5. I drew this, and that's 5 intersections. So 2 is the one that I couldn't make just by method of deduction. There's absolutely no logic going there at all. I was just drawing lines because sometimes that's the most efficient thing to maybe be doing. N is between 1 and 20. If you add up the numbers from 1 to n, you should probably just know that the formula for that is n times n plus 1 over 2. So for example, if n is 10 and you're adding up the numbers 1 to 10, that's just 10 times 11 divided by 2, the answer. So that's fine. Now, Billy adds the rest of them. So the rest of them we need a formula for. And I think the easiest way to find out the sum of the rest of them is just do the sum of the first 20 numbers minus the sum of the ones that you're leaving behind. So I think this is the sum of all the numbers from n plus 1 to 20. That's the sum of the numbers up to 20, and then we're just taking away all the ones up to n. So therefore, this 4 thing here just is the numbers n plus 1 to 20. And now if we set those equal, because apparently they are the same, then we're done. Now, of course, this and this are the same, so just add this to both sides, and you end up with 2 of them, except they're both divided by 2 anyway, so you just end up with 1 of them. This is just 10 times 2, 21, so that's 210, and then you just expand, move over, and you try and factorize this, which, I mean, you can use the answers to help you. You end up here, which means n is 14, I guess, for our answer. And we're good to go. Okay, so large chunk of building blocks. Again, this is another question that I did just by trying stuff. I didn't really have any proper logic, I don't think. Obviously, you can just use 3 4s to make a height of, I mean, this is just an upper bound for the answer, right? Like this is you choose any block for the base, then any other block for the middle, any other block for the top, and you get 27 combinations. Except the answer isn't 27 because that counts things like 4, 4, and then a 4, and then a 4, and then a 6 as different to a 6, then a 4, then a 4. But the problem is that makes the same heighted tower. Well, it makes a tower of height, I don't know, 14 or whatever. So 27 is an upper bound, but it doesn't really work. I just thought listing them was best. This is a 4 4 4 tower, a 6 6 tower, and a 10 10 10 tower. Now that's height 12, height 18, height 30. Those numbers are worth bearing in mind because even if we find a different combination that looks different, if it has the same height, then we can't count it. So this is a different combination, 4 4 6. Now there are 3 of those, but that doesn't matter because they all make a height of 14. And here's another one. They all make a height of 16, which is different to all of these heights, so that's fine. And then this is another one, 6 6 10, and then of course 6 10 6. This makes 22, this makes 26, so that's fine. This is another one, and then of course this makes a height of 18, which we already have in this one here. So that actually doesn't count as anything new. The 4 10 10 makes a height of 24, which is new, and then the 4 10 6 is the last one I counted. So I ended up with 9 in total. We need to use some circle theorems here, particularly the fact that this is a tangent and this is a tangent makes this and this the same, and likewise this and this the same. So we can call this angle here 180 minus beta divided by 2 because these 2 angles are the same. And likewise over here, exactly the same thing's happening because that is the same as this, which makes this angle here 180 minus alpha over 2. And now, of course, this plus this plus this equals 180. And we can just, I mean, it's not too hard to do. Right, this makes a 90, this makes a 90, so all the numbers go away. Minus minus makes pluses. So it's just going to be a half of a alpha plus beta, I think, in the end. This logic question works the same as all the logic questions. You just have to try one day, then the next, and so on. So if they both say yes, they are lies. Let's pretend it's Monday. So this guy's telling the truth on Mondays. So that means he's claiming to be lying on Sundays, which he does, right? It says he lies on Sundays, so that's consistent. Whereas the other guy also tells the truth on Mondays, but tells the truth on Sundays too. So this would be a lie that he was saying. So it's not Monday. Could it be Tuesday? Well, this guy tells the truth on Tuesdays, but he also tells the truth on Mondays. So if on Tuesday he says yes, they are told lies, that's a lie, even though he's supposed to be telling the truth. So it can't be Tuesday. Likewise, it can't be Wednesday or Thursday for the same reason. Could it be Friday? Well, if it was Friday, this guy would be telling a lie. And on Thursday he was telling the truth, so that is a lie, so that's good. And on Friday, this guy's telling the truth, and on Thursday he tells lies, so that would be true. So therefore, it must be Friday as our answer. Yeah, this question I'm not 100% happy with. I reckon Heron's formula might be able to do this. I didn't actually try it, but give Heron's formula a go. I think it might work. I ended up just calling this theta and then saying the area, which is 88, is a half times this times sine theta. Now, this is obviously 10 times 11, which is 110. So that's 88 over 110, which cancels down, I think, if you divide them both by 11 to 8 over 10, which is 4/5, which means that cos theta, just by using sine squared plus cos squared equals 1, is 3/5. You might have just memorized that, except it's actually plus or minus 3/5. We don't really know which. The fact that this looks like an acute angle means that this must be plus 3/5 because cos is acute in that time. But yeah, I'm not really happy with that. I put in plus or minus 3/5 because I wanted to know whether there was some other way that we're supposed to know. So this is just cosine rule, obviously, just with cos theta being replaced with plus or minus 3/5, and then the other stuff, it's just the other stuff. Obviously calculate the rest of this. And now I put a plus minus here because, if this is a minus, you plus it, and if it's a plus, you minus it. And I tried both of them. Now 320 stands out as something that seems easier to do. That's obviously 16 times 20. 20 has a square number anyway, so I guess that's 64 times 5 or whatever. So that's 8 root 5, which is one of the answers. So I circled it. This answer is also legit. It's just not one of the answers on the list, and it's made from an obtuse angle here. So I guess that's why we're supposed to ignore it. But yeah, 8 root 5 is the answer. So yeah. But part of the battle with question 15, I think, is just understanding what the hell is going on. So you've got a big cylinder, and then this kind of line here with the white region beneath it is trying to represent water, which is weird because it's a different color to the water that's represented inside the smaller cylinder. But I guess that's the only way they could think to draw it, which kind of makes some sense. But anyway, you've got some water line in this big cylinder. You've plunged this smaller cylinder in, and as it went beneath the water line, water started tipping in, filling it up from the inside and leaving behind a water line on the top of the cylinder itself, where no more is going in because they're obviously at the same level. So that's kind of what's going on. The way that you can kind of answer this, I just put in all the information that's in the question here, is, well, okay, how much water is in this small cylinder first? Well, it's pi times 25 times 8, which is 200 pi. How much space is being taken up by this small cylinder? Well, it's just twice this, right? Because half of the small cylinder is filled up. So it's pi times 25 times 16, which is 400 pi. So there's 200 pi of water in here and 400 pi of area as the actual small cylinder. So the idea here is, what if you just grabbed this small cylinder here and picked up the entire thing with the water in it and just took it out? Well, then you'd be removing 400 pi of volume. So how much lower would that make the water line, given all the space that the water would be able to flood into once you'd picked out the entire cylinder? Well, there's 100 pi as the area of the kind of face here. So if you're removing 400 pi, you must be removing 4 depth of water, right? Because 4 times 10 squared times pi is volume 400. So if you pick up this cylinder with the water in it, take it out, this drops by 4 to make a height of 12. But then you pour back in half of that. You pour back in the 200 pi of water that you took out as well, and you raise up by 2. So you end up with a net loss of 2 as the height, and you end up with a height of 14, I guess, is the way that I thought about that. Yeah, so this question's kind of interesting. So either red or blue, two, three, or four heads, and there's one of each thing. So there's one red with two heads, one red with three, and so on. So I lined them up red, blue, red, blue, red, blue, and then decided that the only other way to line them up would be blue, red, blue, red. So I'm just going to ignore that and just times the answer by two later. So this is how they're going to line up. And now the obvious way to sort these out would be 2, 3, 4, then well, for the first one. Now 2, 4, 3 is also obviously an option. I'll deal with that in a second. Now let's think about this second set. You've already used your, like here has to be a 2 or a 3, because it can't be next to a four-headed thing. But you've already used your three-headed blue thing, so this must be a 2. And then here, you've already used your red four-headed and two-headed things. That must be a 3, which means this must be a 4. So if you start 2, 3, 4, you have to end 2, 3, 4. Now, is there any other way to configure these? Well, of course there is. You could swap all the numbers around. So I think there are 6 ways to just interchange all the numbers of heads. So, in other words, I've just done 3 factorial there. I've just said the 2's could all become 3's, the 3's could all become 4's, and then so on and so on. Just do all the swaps. There's 3 choices for what? If you call this star, this hexagon, this pentagon, there are 6 ways to arrange those because there's 3, then 2, then 1 choice. That's massively overcomplicating it, I guess. I don't know. 3 factorial, we can swap them over. Just just believe it. Cool. That's good YouTubing, right? That's good YouTubing. It's 3 factorial because I say it is. Now, the only other way to configure these, though, would be I think there is an extra choice. No, sorry, there are no extra choices at all. It's just the times 2 because you could go blue, red, blue, red, blue, red, right? So you have the initial setup. There are 6 ways of changing the heads around, and then there are 2 ways of changing the colors. So I think that's 12 in total. Yeah, that's it. Cool. So biggest circle is radius 1. So that's 1. And then this is also 1. Now, this distance here, sorry, yeah, so that's distance 2. Now, this distance here is 1 to this edge. And now this distance to there, just below this center line, is little r, where little r represents the little radius. Now, you can do the same going upwards, which makes a right angled triangle of length r plus 1, and 2. So now we can just do Pythagoras. All right, so expand all the brackets out and collect. Divide everything by 2, I guess. Take away 2 from both sides. This immediately, I know, has this answer because it's the only answer it could possibly be, because this is some kind of quadratic that doesn't have nice solutions. So it literally can't be anything other than C, and I couldn't be bothered to solve it from there. So 10 factorial is what it says it is. The trick to answering questions like these is to write 10 factorial as a product of primes. So how many 2's exist in 10 factorial? Well, there's 1 there, 2 there, 1 there, 3 there, and 1 there. That's 8 in total. So that's 1, 2, 3, 4, 5, 6, 7, 8. How many 3's? Well, there's 1, 2, 3, 4. How many 5's? Well, there's 1 and 2, and then 7's, there's just 1. So 10 factorial is this in prime factorized form. K squared is a factor of this. So we're looking for a square number, and a trick to know here is that square numbers must have even powers in their prime factorization. Otherwise, you couldn't square root them cleanly, because when you square root them, you'd halve the powers, and the powers of half the halves, or to 0.5s, and that's like a third. So K squared has to have even powers, and the biggest even power thing you could put in here is just this without the 7. So I think K squared is this. So therefore 7 times K squared is 10 factorial, and therefore K squared is a factor of 10 along with its pair of 7. So K squared is that square root, like I said, just halve all the powers, and K is this thing, which is 16 times 9 times 5, which you just need to work out, I think is 720. And we're good. P, Q, and R in a straight line like this, so that's pretty cool. Length of, we'll just call length of X for the smallest one. The middle has sides 8 centimeters longer, so that means this side is 8 plus X, which means this little bit here is 8, and this is 8 plus X, as we said before. Now, moving on, the largest square has side length 50, which means that we could call, well, let's call this length Y for a second. Now, these two triangles must be similar because they're on a straight line. So I think 8 divided by x equals y divided by 8, x plus 8. And now let's rearrange this for y, to get this. And now I think we could say that because this side, or this square, has side length 50, I think this little y, which is this, plus x plus 8 must be 50. And that's an equation of x. So times everything by x, and then we can just put things together, and that eventually factorizes for those two answers there, and we're good to go. So a square ink pad, so there's my square ink pad, has side length 1, so that's 1 by 1. It's placed on a big piece of paper and rotated around 180 degrees by one of its corners. So it's rotated by a corner. 180 means it either goes this way or this way, and it ends up being there. Now, this, if it's 1 by 1, this distance here is root 2, and that's important. That's this distance here, I'm kind of saying. Because when you swivel this around, and you could even, since you have paper, you could try this. You could rip up a piece of paper and try it in the actual challenge, or just now if you're not doing the challenge. When this rotates around, it's going to create a semicircle of color. Like it's going to sweep a black circle like this. And this is all going to be black, along with, of course, this initial bit and this bit over here. So we now just need to work out this area, which is a half, because it's a semicircle, times pi times root 2 squared to get this bit, and then just plus this and this, which obviously make 1 because it's just like the initial square, right, together. And we end up with this pi plus 1 answer because the 2 and the half cancel. And we're good to go. Yeah, so question 21. So we'll call this x and this x and this x, and then we'll put the numbers in the question in as well. Now, this triangle is clearly a smaller version of the big triangle because of parallel and stuff. So this triangle is a smaller version of the big thing. Now, the corresponding sides are x and 2. So the scale factor to get from small triangle to big triangle, I think, is 2 over x. So if I times the small triangle by 2 over x, because x times 2 over x is just 2, I'll get big length of 2. So therefore, y times 2 over x is this length here. Y times 2 over x is this length here, right? Because y is the smaller base to the bigger base. So y times 2 over x is just this length of 4. So therefore, y is 2x, just timesing both sides by 2, by x, and then divided by 2. So this length is 2x. Likewise over here, let's do exactly the same thing. Let's call this z, and the scale factor, for very similar reasons, is 3 over x, which means z times 3 over x is 4 again. Divide by 3 and times by 4, and we get this. And now we can say, because this length here is the same as this length here, and this length here is the same as this length here, we have 2x plus 4/3 x is this 4, and we can solve that pretty quickly for x. We'll end up with this, I think, as long as I haven't made any mistakes. The last few questions then, this looks like a functions question where you have to do something intelligent, but it's not. It's literally just an algebra question. Let's just put this algebra in a more simple way. So I grouped this entire first 2 terms together just because it looks a bit like these last 2 terms. So group all this together and then treat it as a fraction, times it by this denominator over itself. Right, so I'm just taking this as one object and timesing it by this over this to make the denominators the same. And now this times this is x squared, middle terms cancel, and then minus the roots cancel, so it's minus brackets x squared plus 1. And this is obviously the same. Now the x squareds cancel, and also minus 1 plus 1 is 0. So the whole thing is 0. So the whole thing is 0 regardless of the input. Easy. Next, given 4 non-zero digits, so I'll just call those digits a, b, c, d. You can make 24 of those. Well, agreed, it's just 4 factorial. So that's agreed. Cool. What's the largest prime factor when you add all of these numbers together? Okay, so I'm not going to list all these numbers out. But there are 6 of the, if there are 24 numbers of this type in total, that means 6 of them start with an A, because A is a quarter of the letters, 24 over 4 is 6. So 6 of the combinations start with A. It's also just A, and then there are 6 ways to mess around with those, so there's clearly 6 of them. So 6 start with A, 6 start with B, 6 start with C, and 6 start with D. So if I imagine adding together all of these numbers, if I just imagine adding together the thousands digit, there are 6 copies of A to add together, 6 copies of B, 6 of C, and 6 of D. But also, each one of the digits is worth 1,000 because it's the 4th thing along. So I think that would make 6,000 A plus B plus C plus D. 6 coming from the fact that there are 6 of them in each of all the combinations, and then 1,000 because they're worth 1,000. Likewise, for the second digit, there are 6 of them that would have A in the second digit, and 6 that would have B, and so on. They're all worth 100 this time. So if I were to just add that column together, I'd get this. And then the C's, the third column, likewise, the 4th column, likewise. Now we can obviously just factorize out the A plus B plus C plus D and just end up with, or we can just say there's 6,000 lots of this plus 600 plus, and you end up with this. And now this thing obviously factorizes to 1, 1, 1, 1 times 6. And 1, 1, 1, 1 kind of semi-obviously factorizes to 11 times 101, and n I've just said is a plus b plus c plus d, which I know is less than 101 because it's at most 9 plus 8 plus 7 plus 6, I guess. But yeah, 101 will therefore be the biggest prime factor, I think. Peter has 25 cards, each printed 1 to 25. He wishes to place n cards in a row, so that every card has a prime factor in common. Cool. Now, the first thing we'll say here is which cards cannot be part of this game. Well, 1 doesn't have any prime factors, so it can't share any prime factors with any other number because it doesn't have any. So 1 cannot be part of this game at all, and neither. Now, something like 7, which is prime, can be, because it can go next to 14. It can also go next to 21, so that's fine. And 11 can go next to 22. But the moment you pass that, 13 is prime, and its next thing that it shares anything with would be 26, where it would share a 13 in common. But 26 is not part of this game. So I think 13 can't be part of this game. And likewise, every other prime number above the halfway point won't be part of this game, because the next multiple of it isn't part of the game. So we can't use those 5 cards. So therefore, if there are 25 cards in total, the upper bound of how we can do this is 20, because we just can't use these 5. Now, at this point, you have a choice. If you're low on time, you just underline 20 and hope that it's possible to put the cards together to make 20. If you've got loads of time, you actually bother to make a list that looks a bit like this, which I hope works, and you say, therefore, the answer is definitely 20. The very last question, then, always love these function questions. I just think they're great. So we have this function wall here. That means f of 10, because 10 is 10 times 1, for instance, f of 10 is f of 10 plus f of 1, but that of course makes f of 1 0. And up here I'll just list all the things that I've learned from doing various trials with this formula here. Now f of 10 is also 5 times 2, so it's also f of 5 plus f of 2, and now f of 10 I know is 14, so at 14 is whatever this is plus whatever that is. Now f of 40, now 40 can also be made with a 5, so that could be something we could use. It's 5 times 8. So it's f of 5 plus f of 8. Now, f of 8 is f of 2 times 2 times 2. So therefore, I'm just writing, I'm assuming this works with 3 of them. Why not? So 2 times 2 times 2 is f of 2 plus f of 2 plus f of 2, which is 3f of 2. Okay, well, I think this is now something that's great, right? If we just do this, take away this, we get 2f of 2's is equal to 6, which means f of 2 is equal to 3, which also means that f of 5 is equal to 11. Cool. Now, I think we're pretty much done here, because 500, I think, can be written as 5 times 5 times a bunch of 2's. No, times another 5. 1, 2, 5 times 4. Yeah, fair enough. Because 100 I know is 2 squared times 5 squared. So then you just times it by another 5. Yeah, cool. So by using this rule on steroids, I think this is just f of 2 plus f of 2 plus f of 5 plus f of 5 plus f of 5, which is just this. And we have our answer of 39. And that's the entire paper. Thanks for watching.